Some years ago, we started to develop a methodology based on quantification of orientation and alignment of components of a ceramic body as one of the principal features reflecting pottery-forming techniques that are theoretically observable on every shard. We focused on the quantification as a way how to refine the analysis of preferred orientation by defining exact intervals of orientation variability for the individual forming techniques and their combinations. For the measurements, we used two basic sections perpendicular to the wall surface in the plane parallel to the vessel height. I will call them radial sections, and sections tangential to the vessel wall cut through a core zone of the wall. I will call them tangential sections. Originally, we captured 3 transects approximately 6 mm wide in each thin section at the magnification of 40 times in plane polarized light using a standard petrographic microscope. The resultant images have a resolution around 1 micrometer. Then inclusions and voids were extracted using object extraction and separation methods in J Microvision software. The object extraction and separation process yield a map of random plane sections of inclusions and voids. These areas were characterized by a set of descriptors relevant to the analysis. The most important are elongation, calculated as aspect ratio, and orientation. The object with aspect ratio 1 to 0.6 were selected for the analysis based on the examination of the relation between elongation, size, and the expected alignment of the object. The object orientation is represented by 2 basic descriptors. Mean direction, which represents average orientation of objects, and circular standard deviation, which represents the dispersion of the values from the average. In the first experimental collection, we found several significant markers distinguishing wheel finishing, wheel shaping, and wheel throwing as basic levels of contribution of rotational movement in pottery forming. For example, in mean direction in core areas of radial sections, as you can see here on this slide, in circular standard deviation in core areas of radial sections, or in mean directions in tangential sections. In the second dataset, we focused directly on the distinction among different uses of potter's wheel. In this dataset, we evaluated the effect of the degree of transformation of the clay mass, the shape of the vessel, the velocity of rotation, or the individual experience and skills of the potter. We also changed the way of plotting the data, which allows us to compare the combination of the 2 basic parameters, mean direction and circular standard deviation. The raw data are plotted in a polar coordinate system. Each point in the diagram is determined by an angle from a reference direction, which represents mean direction of the objects of the given sample, and the distance from the center of the circle, which represents circular standard deviation values. The points more distant from the center of the circle have less aligned microstructures. The calculated orientations are an axial type of data. Axial data consist of an undirected line. Either end of the line could be taken as the direction. Therefore, the data are represented by both possible directions, which means that each sample is plotted by a pair of points. What were the principal findings of analysis of this collection? Appearance of objects in the marginal zones of wheel-thrown pottery incline inwards towards the core of the wall. We discovered this phenomenon during the analysis of the first collection. We call this phenomenon imbricate pattern and suggested that this pattern is caused by shear stress induced by upward movements of the fingers during wheel throwing. The clay mass in the margins moves more quickly during lifting than the mass in the core of the wall. Therefore, marginal zones can be seen as shear zones with a predominance of shear stress. Comparison of internal and external areas show that the inclination of the object inwards is more strongly developed in the external zones. We explain this phenomenon by the disproportion of the forces required on the interior and exterior of the vessel, which causes larger shear deformation on the exterior area of the vessel wall and subsequently a more pronounced imbricate pattern in this area. The specific characteristics of the orientation of wheel-thrown samples are developed especially in the lower parts of the vessels. You can see it on the radial sections here. However, a significant difference between the results obtained from lower and upper parts of the experimental vessels can be seen especially in the tangential sections. It is clear that the lower parts reflects the primary forming techniques more accurately than the upper parts, and this is especially true for wheel throwing. This difference is a consequence of a throwing process. First, a lump of clay is centered on a wheel head by a series of upward and downward movements. It is then opened in the center. An inside base is formed and the wall of the vessel are lifted from the remainder of the clay by a series of upward movements. The preparation of the base before lifting requires strong deformation of the clay at the base of the wall. When the potter transforms the lump of clay into the form prepared for lifting. While she or he lifts the clay mass upward, the rest of clay is lifted above the fingers, but is not affected by their movements, and thus the rim itself, last remnant of the clay, is practically unaffected by the lifting movement. Consequently, very poorly developed throwing structure can be observed in this area, and in some cases, even orientation with the opposite deviation from the horizontal plane was calculated, probably as a residuum of the initial centering of the lump of clay. The analysis of the second collection has shown that wheel throwing can be differentiated from other applications of rotational movement in forming, but characteristic orientation parameters are not independent of the context of the manufacture. They reflect the equilibrium established between the movements of the potter's hands, the technical parameters of the rotational device, the clay properties, and the shape of the vessel. If the potter uses unfamiliar clay or rotational device or throws an unusual shape, he disturbs the equilibrium gained by the experience and thus also the alignment typical for the technique. This especially applies to the beginner for whom all the components of the technique are new. It seems that shape significantly influences the orientation parameters. Samples taken from the oblate ellipsoid show below average standard deviation values in radial sections from the lower parts of the vessel, but more importantly, a significant increase in deviation and lesser deviation from the horizontal axis in tangential sections. The distortion from typical wheel throwing values for conical shapes could be hypothetically proportional to the degree of transformation that is required to finish the shape of the vessel extra to the lifting of the clay. The third experimental collection was prepared based on the findings of the analysis of the second experimental collection. And this experimental collection was focused solely on the variability of orientation patterns within wheel throwing method. So far we employed one principal experienced potter, Peter Thomas. We would like to know whether the results will be similar also when measuring products of other professional potters. Thus, along with Peter, we included two other professional potters, Henry and Thomas. The second question was related to the hypothesis that a complicated shape, it means shape that requires more movements than simple shaping by lifting of clay, cause distortion of the typical orientation pattern. The assignment for the potters was as follows: to throw 15 slightly conical pots and 15 S-shaped balls. This shape was chosen because in our application of the methodology we are dealing mainly with late Iron Age pottery in Central Europe, and it is the most common shape of wheel-made pottery in this context. The target wall thickness was for all containers was 5 mm. No other parameters of the forming method were specified, with the aim not to force the potters to employ the actions which are not natural to them. All potters used their wheels and the same fine-grained commercial clay. Also, the dataset was complemented by 6 conical vessels thrown by Peter on a flywheel. In the analysis, we focus on tangential sections, which are more informative. The results of the analysis were surprising. Each of the potters produced a different pattern. We start with Peter. The pots show coherent group corresponding to our previous findings in orientation and alignment. But balls exhibit similar orientation with significant increase in circular standard deviation, with extreme exceeding 40 degrees. Throwing of pots on flywheel shows a decrease of deviation from the horizontal axis, which is significant compared to conical pots thrown on the standard potter's wheel. In the production of Henry, we are not able to differentiate reliably between pots and balls. Both show higher average deviation from horizontal axis. And then Peter's vessels. Average circular standard deviation is similar and comparable with balls produced by Peter. Only a small proportion of pots show circular standard deviations below 30 degrees. Both the shapes manufactured by Thomas show lower average deviation from the horizontal axis, and there is a significant difference between them in this respect. Balls demonstrate lower deviation than pots. Thomas' vessels are very similar in alignment to those of Henry. For now, we are far from understanding what causes the differences. As usual, the answers are not as simple as we usually hope in the beginning. On the other hand, what is exciting is the orientation pattern. This is that the orientation patterns can reflect the style of the potters using the same forming method that seems to be very deterministic in terms of the forces employed during forming. What is less exciting is the increase in the number of factors affecting the orientational patterns, which prevents its application without pre-understanding of the basic technological variability of the studied archaeological assemblages. We have to work more carefully with the limits of orientation typical for individual forming techniques. During the third experimental collection, We used Keon's digital microscope instead of a petrographic microscope. This significantly speeded up the whole analysis process and increased the quality of the recorded images. The entire area of the thin section is recorded by the sequence of the images captured at magnification 200 times, which are automatically stitched together. The resultant image of the entire thin section has a similar resolution, and when capturing by the petrographic microscope, it means around 1 micrometer. The components of the ceramic material were extracted uses automatic area measurement tool available in the Keon's measurement software. The range of threshold values chosen to separate objects was based primarily on color saturation, which shows the best results for the thin section with an uneven thickness, resulting in uneven brightness of the captured image. Finally, we are considering the substitution of optical microscopy of thin sections by X-ray computed tomography scanning. The advantage of the CT scans is that they represent the whole solid, which means better control of the section positions, the possibility to work with multiple sections, or even the possibility to calculate geometry in three-dimensional space. The theoretical advantage is also non-destructiveness of the analysis. However, there are several difficulties of the use of CT scans for the quantitative analysis of orientation in the current stage of technological development. Quantification of the textural phenomena of fine-grained ceramics is complicated, as small voids and particles require high resolution. Because the scanned sample needs to be rotated close to the Röntgen source to achieve high resolution, usually the size of the ceramic shard has to be reduced to meet the required parameters, and thus the analysis becomes destructive. We attempt to use micro-CT for fine-grained materials, which were used for most of the wheel-made pottery during late Iron Age in Central Europe. Thus the resolution of the CT scan is crucial for us. Currently, we use high-resolution 3D X-ray microscope SkyScan. In attempt to reach a resolution similar to the resolution of thin section images, we need to reduce the size of the sample to approximately 10 millimeters. The only advantage in terms of destructiveness is that we do not need to cut two samples from two sections, just one for the scanning. With such sample, we can reach the resolution of 3 micrometers after approximately 20 hours of scanning. Size of the resulted dataset is approximately 100 gigabytes. Another difficulty is common to all X-ray techniques. The method is well suited to an investigation of porous structures within shards because of the high density contrast between solids and voids. On the other hand, the density contrast between a majority of non-plastic mineral particles and the clay matrix is often low, and it is difficult to visualize them clearly, especially for the purpose of the quantitative analysis. That's all for me, and thank you for your attention.